Welcome to Dr. Cass's virtual reality planetarium. You are in a field just outside Athens, Georgia. Look around you. Forward, left, right, up. Look straight ahead again. The red letters you can see on the horizon indicate direction. If I tell you to look north, look straight ahead at north. Look to your right, that's east. Look to your left, that's west. So this planetarium is pretty good, but we can make it better. Why don't we go ahead and remove the atmosphere? That way we don't get any scattering of the light as the photons travel through the atmosphere. Look around. The stars are much more clear now. You should also be able to see patterns of dust throughout the sky. We can do a little bit better. Why don't we go ahead and remove the ground? Now we can see the whole sky, since planet Earth is no longer blocking our view. You can see the sun below the horizon. You can see the Milky Way if you look to your east and look below. That is the plane of our galaxy, the centre of our galaxy that contains the majority of the mass, the gas, the stars, the dust in our galaxy. Let's get our bearings. Look straight ahead again. I'll draw in some constellations for you. Look around. These constellations are the Western culture constellations, the one that we use in our astronomy course here at UGA, but there are many others throughout the world. Look north. I want you to find Ursa Minor, also known as the Little Bear. If I draw in the constellation art for you, it should be a little bit easier to find. If you look a little further up, you can see Ursa Major. Look down again at Ursa Minor. I'm going to remove the constellation art now. The tail of Ursa Minor contains the star Polaris, also known as the North Star. The tip of the tail, this North Star, is really helpful because it is very, very close to the point at which our entire celestial sky rotates around. Now, let's speed things up and watch how the night sky rotates around Polaris. Let's speed things up a little more. Our night sky appears to rotate, but it only appears to rotate because, of course, planet Earth is rotating. Let's stop this. Now, if I tell you to look north or east or west, it's fairly easy for you to do. Go ahead, look north, look east, look to your west. It's pretty intuitive. So astronomers put a system like this onto the night sky. It is called the Altitude Azimuth Coordinate System. We call it the ALTAZ for short. That's the grid that I've projected onto the night sky that you can see here. Look directly over your head at the zenith, which is the point directly above your head. Now look down to the horizon, follow those grid lines. This is a very useful coordinate system. It's very intuitive. If I tell you to look east, look about 20 degrees above the horizon, you should see the star Altair. It's pretty easy for you to do. However, this grid is specific to your location on Earth, specific to your latitude, which is how far north or south you are of the equator, and also your longitude, which is how far east or west you are of Greenwich in London. Now, if I speed up the night sky once again, what happens to the stars? You can see the stars are moving through this grid. Pick a star in the night sky, focus on it. Its position is changing. It's no longer being described by the same point in the grid, with the exception, of course, of Polaris, because that is located at the point at which the entire night sky rotates around. Let's remove this grid. Since the Earth moves around the Sun, as well as rotating on its axis, stars rise about 4 minutes earlier each night. Because of this, the stars aren't always in the same place night from night at the same time. Since the Earth moves around the Sun, as well as rotating on its axis, that's what causes this effect. So let's rotate our view so that we're looking south now instead of north. Don't worry, I'm going to move for you. You keep your head still. You should be looking south. Let's head to a time about midday. So I'm just going to fast forward things a little bit for you. If you feel a little motion sick, you can go ahead and close your eyes. Here we are at midday. You can see the sun in the sky. Now, let's advance by 1 solar day at a time. So, 1 solar day is 24 hours. It's the time it takes for the sun to be in the same position in the sky again. So it's directly overhead. You can see the sun is changing its position relative to the background stars. The reason for this is it actually only takes planet Earth 23 hours and 56 minutes to rotate 360 degrees. A solar day is longer than a sidereal day because planet Earth has to rotate a little further to line back up again with the sun. So here is our solar day, 24 hours. Now, our sidereal day is the time it takes for us to line up again with the background stars. Here I am rotating by 1 sidereal day. Look how the sky remains the same, but the sun does not, nor does anything else in our solar system. This is 1 sidereal day. You will notice that the sun was moving on a path through the sky. Let me draw in that path. This is called the ecliptic. It is the path that the sun follows simply because we are in orbit around the sun. Now, there is a much better coordinate system that we can use where the stars stay fixed. It is called the equatorial coordinate system. I'm going to project that for you now. The celestial equator projects outwards from the equator of planet Earth. The declination of an object is the degrees north or south from this celestial equator. And this is analogous to latitude on Earth. The right ascension of an object is analogous to a longitude. Just like on Earth, where we pick Greenwich in London as our arbitrary starting point, we need a starting point on the night sky. This is called the vernal equinox. It is where the ecliptic, or the path of the sun, intersects the celestial equator. It happens on midday at the spring equinox, which is the 20th of March. Now, I'm going to speed up time. What do you notice? Our equatorial grid is moving. It is moving at the same rate as the background stars. This means we can find things on the night sky. These objects don't move relative to the grid. Let's bring time back to its usual place. have a good look around. And thank you very much for coming to Dr. Cass's virtual planetarium.